Okay, so we reached the point where we're at continuous functions, and that's really when we start to see topology as something. So you've done structures, right?
Yeah.
So you're used to the whole idea of a mathematical structure as kind of being, you can think of it as just like points and arrows. So the points are the things you study. They could be groups, rings, topological spaces, and the arrows that go from between them are functions of some kind. So in group theory, it's homomorphisms. In ring theory, it's ring homomorphisms. And in topological spaces, it's continuous functions. And so you can't really get a full grasp of what topology is until you have those arrows that join one topological. So the natural thing to go from one topological space to another is a continuous function. And then with that, and so you also get all the other structure. So we've started looking at, you have an object, you have a sub-object, whether it's a subgroup, subring, subspace. As I said, you have the natural maps. So for us, it's continuous functions. From them, it gets things like quotients. You need a function to be able to define a quotient. So we'll be able to do that later. Okay. So the topological definition of continuity is a little bit different from what you're used to, because in calculus, you're used to the epsilon delta definition, and that comes about because we've got distance. So have you done advanced calc?
Yeah.
So you know about metric spaces?
I don't think we...
Oh, you don't? Oh, well, I mean, metric spaces are just spaces with a distance. And once you've got a distance, you get lots of nice, you can define lots of nice things. Continuity and convergence sort of have like these nice natural definitions. In a topological space, you don't necessarily have that idea of distance. You do have the idea of neighborhoods. And that's kind of what you use instead. So for us, a continuous function is a function such that the inverse image of every open set is open. Okay, now that might seem a little strange. You might think, well, shouldn't it be the other way around? Shouldn't open sets go to open sets? And there's good reasons why that just doesn't work. So for example, not all continuous functions are open functions, and not all open functions are continuous. So for example, a nice function like x squared, right? Well, what is f of the open interval minus 1, 1 going to be?
0 to 1.
0 to 1. Closed, right? So so this is a nice function, and you want to include that. To get an open function which is not continuous, you have to be a bit devious, but here's an example. F of x equals the summation I equals 1 to infinity of minus 1 to the xi over I, where you write x as x1, x2, x3 in its binary notation, something like that. So this is a really weird little function. You notice that you're dealing with the harmonic series. And do you remember a theorem that says that if you've got a harmonic series, but you can play with the sign, like the alternating harmonic series. If you, remember it's only conditionally convergent, right? By manipulating a little bit, you can actually make it equal any number you want. So if you look at the image of this, you can actually, by the appropriate binary number, you can make this any number you want. So f of any open interval, we'll see later that the open interval is basically homeomorphic to R. You can take any open interval, its image is actually going to be the entire real numbers, because within that you're going to be able to find a binary number so that so you can make this thing converge to whatever you want. And this number here it's obviously not continuous, right? It's continuous at no point, but it's an open map. So that tells you that, well, this is just giving you some idea why the idea of F open being open doesn't work, but it turns out that the inverse of open being open really work. It is the right thing. And we'll see later things falling into place. But that's why. Now notice whether a function is continuous or not only depends upon the function, but on the topological spaces. It's the actual topologies of what is an open set, right? Because you've got the inverse image of an open set is open, so that depends upon what topology you've got on X and Y. So functions can be continuous in one topology, but if you change the topology, then it's not going to be continuous. Okay? So for example, in the discrete topology, every function is continuous. I mean, sorry, you've got the discrete on both of them. Oh no, actually, you just need the discrete on X.
Right, because every inverse image of any set is
Right. So, and if you've got the indiscrete topology, it's hard for things to be continuous now. So it depends upon the topology. So that's the important thing. An important thing to note is that we say here inverse image of an open set is open, but one of the useful things, if you've got a basis element, then if the inverse image of every basis element is open, then the thing is open, and that's because you can just write any open set as a union of basis elements, and the inverse image of that is going to be, so if each basis element goes back to something open, then you take the union of that thing, you're going to get something open. And that's also going to be true for sub-basis elements, because you can do the same thing with intersections then. Since any basis element is the finite intersection of sub-basis element, look at the pre-image of that. Because the thing is nicer than F in set things, right? Because F of A union B is F A union F of B, but F of A intersected B, there's just the inclusion one. Do you remember which way it goes? Is it?
I think it's that way.
F inverse of A intersected B actually is F inverse A intersected F inverse B. So inverse behaves much nicer. And I think the same is also true for complements, like F inverse of A minus B is F inverse of A minus F inverse of B, but that's not true for F. Okay, so another hint maybe of why dealing with the inverses is kind of nicer.
Are we saying that when we say every basis element of Y or every basis element contained in the range of F? For two.
Of the range Y, yes, because it's saying of the range in Y. Sorry, I should say.
Okay.
Yeah, it's yeah, you're right. We're only interested in the range, right?
Right.
And we'll see that later. We'll have theorems about that. So the first thing to note is that the epsilon delta stuff that you've seen before is actually equivalent to this definition. And that's because if you think about the epsilon delta definition, you can turn that into something talking about basis elements, right, in R. Because what's a basis element in R? It's just an open interval AB. So, you know, saying F. So what are we saying? So I wrote this down because I wanted to not get mixed up by that. Right. So why does our definition imply the epsilon delta definition? Okay. So what do we got? So so we want to show that it's continuous at some point x naught. And so what does the epsilon delta argument say that? So it says given an epsilon greater than 0, what does it say? There exists a delta greater than 0 such that f of x, what is it, is whenever x minus x naught is less than delta. Okay. So what does this? So if our definition is true, then so what this is some open set, and so we can have a look at f x naught minus epsilon f of x naught plus epsilon. That's an open set, which means that that its pre-image is going to be some open set. So there exists some x naught minus a x naught plus b. Hang on. So the pre-image of this is an open set. So it definitely contains basis elements. Basis elements look like this. So there's got to be some open interval that lies in the pre-image. And so then we just take delta to be the minimum of x naught minus a and x naught the minimum of a and b, I guess. I put it that way. Right, so this is open. Its pre-image is open, so therefore its pre-image contains a basis element, and then we can knock down the basis element to get our delta. And then going the other way, why does epsilon delta give our definition? The easiest way to do that is argue by contradiction. Let's say U is open and F inverse of U not open. So what does that mean? So that means there exists an X naught in the pre-image where every neighborhood of X naught contains points outside of our open set F inverse. And then you can then get a contradiction of that using the epsilon delta argument there. So that actually works out. So in your multivariable calculus, you've met lots of continuous functions. So things like curves in two-dimensional space or three-dimensional space. That's going to be a function from R to R2 or R3. And you talked about those being continuous. You would talk about multivariable functions, like functions from R2 to R or R3 from R, and you would talk about them being continuous. And you would also talk about vector fields, which is a function from R2 to R2. You would have talked about those being continuous. All those have the same continuity there, means continuity in our definition. So here's an example where topology matters. So this is the identity function from R to R, but let's put different topologies on R. So remember R sub L was the lower limit topology, where we included as open sets, sets where the lower limit could be closed. And so straight away you can see what the problem is. The lower limit topology is finer than the standard topology on R. So there are open sets in here which are not open in R. And so if you take a pre-image of that, it's going to be open here, it's not going to be open here. So for example, 0, 1, its pre-image is the half open interval 0, 1, and that's not open in R. So this map is not continuous, but this identity function is going from R back from the lower limit topology to R, because now anything that's open here is going to be open in the pre-image. So that sort of basic example shows that topology kind of matters. Okay, so it's useful for us to have equivalent ways of of figuring out whether a function is continuous or not. So the following are equivalent. Function is continuous if and only if every subset of A, the image of the closure is contained within the closure of the image. Oops. Mistake here, that should be closed. It's also equivalent of saying that the pre-image of closed sets is closed. And there's also sort of kind of like a local definition of continuity, where you just look at a point and each neighborhood of the image of that point, then you want a neighborhood of our point such its image is contained within the neighborhood of the image. And so that gives you the idea of just being continuous at a single point. If it's true just for that point, then it's continuous at that point. So let's have a look at that. I need to bring in more talk. Rapidly running out of talk. So let's show that 1 times 2. So we're given that f is continuous. And so what we want to show is that if x is in x is in the closure of A, then f of x is in the closure of the image of A. So this is for f is continuous, and let's just say A be some subset of x. Is that true then? X is in the closure of that. Right, that's exactly what we want to show. Okay, so how do we go about showing? So let V be a neighborhood of f of x. Then, since f is continuous, the pre-image of V is a neighborhood of x. So remember, a neighborhood is an open set containing that. So f, the pre-image of V, if we intersected A, has to contain some y. So that tells us that f of y is in V intersected f of A. And that does it for us. Next, Let's do 2. Okay, I think that does it. Okay, so let's let B be closed in Y and let A be the pre-image of B. So what do we want to show? We want to show that A is closed. That's what condition 3 says. So the way we're going to show that is by showing that the closure of A is A. So f of A equals F inverse of B, which contains B. So if X is in the closure of A, then F of X is in the image of the closure of A, which by 2 is contained within the closure of the image. So this is where we're using the hypothesis, which is contained within the closure of B, because of this thing over here, which equals B, because B is closed. So X, so X is in what did I do wrong here? Oh, so this tells us that X is an element of F inverse B. So we started off with X being in the closure, and we've shown that X is in the A itself. So therefore,
The
A.
closure of A is a subset of A, is what that line is doing.
So which one here?
The second to last line.
This one here?
That's all just amounting to the closure of A as a subset of A, right?
Right. So this is by the hypothesis that's true.
Okay, and then it follows that they're equal.
Right. Right. Because this thing here is contained within here by this statement here, and B is closed, so that's there. Why does 3 imply 1? Yes, I'm going to do 3 applies 1. So what was 3 again? 3 says that the pre-image of pre-image of a closed set is a closed set. So V is open in Y. Let B equal Y minus Z. So if B is a closed set of Y, then it's the complement of an open set. Then F inverse of B, the pre-images are well behaved, so this equals F inverse of Y minus F inverse of B, which equals X, so minus F inverse of B. So this is closed. So this is closed by hypothesis 3. But if this is closed, this means that F inverse of B is open. So that's 1. So it's just using the fact that closed is the complement of open, and the fact that complements are well behaved under taking inverses of functions. Okay, and the last thing is to show that 1 is equivalent to 4. We need to show 1 equivalent to 4 and 4. But this one's probably the easiest of the lot, because remember 1 means F is continuous, and 4 is kind of like the local definition of continuity. If X is an element of our set, and V is a neighborhood of the image, well, we take the pre-image of a neighborhood of the image, that is a neighborhood of X. Because 1 by 1 the function is continuous. So going from the global to the local is very straightforward. I guess the harder way is to go from the local to the global. Okay, so we want to show that a function is continuous, so we've got to show the pre-image of an open set is open. So let V be open in Y, and let X be in the pre-image of that open set. So what we want to do is show that this set is open. Well, if X is in the pre-image, that means F of X is in our open set. And so by 4, using the local condition on continuity, there is a neighborhood U sub X of X such that F of UX is contained within V. So that means UX is contained in the pre-image of V. But now we can just take arbitrary unions of all these neighborhoods, and that gives us that pre-image is this union, but an arbitrary union of open sets is open. And so we can go from the local to the global because arbitrary unions of open sets are open. Okay. Excellent. Okay. But once we have functions, we can have the idea of an isomorphism, which is like a really key idea. So that's the other thing that comes once you've got your points and your arrows. So the idea that two structures are the same, and basically all we've done is just rename, we can just relabel all the elements in the space, and in some sense it's the same space. So you've seen that with isomorphisms and groups and rings. In topology, we call that a homeomorphism. So what do we want? We want a bijection, and we want both the map and its inverse to be continuous functions. Okay, now if you think about it, this cleans up the problem with why aren't open maps what we want to do with, right? Because if both of these are continuous, then these maps are both open. So you want both the inverse and the function itself to be continuous, and then everything is open and closed. And also you can kind of see how this gives us the idea of this kind of rubber sheet geometry that we kind of think. So let's say, here is our space. It's a square with a hole taken out, and here are some open sets. And so with our homeomorphisms, we can go back and forth with something that might look like here's f of u1, f of u2, etc. And so this is this whole idea of the rubber sheet geometry kind of thing. We can go for it, and we can somehow deform the thing that is a continuous deformation. And so now we've got the concept of a topological property. So some properties are, a space can have some property, and if it's a property which is preserved whenever you do a homeomorphism, then you've got the idea of a topological property. So for example, this hole that we've got here is going to exist in all spaces which are homeomorphic to our space here. So that hole there is some topological property. Whereas the fact that here we've got nice 90-degree angles here, that's not going to be preserved under the homeomorphism. So angles is not a topological property. Whereas things like connectedness, compactness, holes, those kind of things. We can make it more rigorous, the idea of a hole. That's the whole thing. Topological properties is really what you are studying. Another kind of important concept is the concept of an embedding. So you've got a topological space, two topological spaces, you've got a function from one into another, and it's an injective continuous map. And so what we can do is we can restrict the range, right? So it's the same function, but instead of y, we're just looking at the image of the function there. So it goes from being an injection into being a bijection. Right? So if that happens to be a homeomorphism now, then we call that a embedding. More strictly correctly, it's a topological embedding. So for example, we can think of R being embedded into R2, for example. And again, this turns out to be a really useful, I should have bolded those things there because that's rough defined. Okay, so let's have a look at some examples. So a really simple example here. The first one, f of x equals 3x plus 1. And we can solve for its inverse. So you remember how to solve for inverses, right? Let this be y. And now we solve for x. Right? And this can easily be seen to be a bijection because f inverse of x turns out to be x, and f inverse of f of x also turns out to be x. So it's very easy to show that that's a bijection. And it's continuous. We can just appeal to the normal calculus definitions. Epsilon delta, that's continuous. So this gives us a homeomorphism. So it's you might call it an automorphism of R. Next one's a little bit more interesting. Where's my glasses? It shows that the open interval -1, 1 is homeomorphic to R. And I know, had you seen that before? Somehow it's kind of like isomorphic. Yeah, it has the same cardinality. So as topological spaces, they're the same. Okay. And to see that here is actually functions which give that homeomorphism. So here's f of x y, and again, you can invert that. Takes a lot more work. Basically, right, I'll solve, you go quadratic equation and you solve it and you just take one branch of that. So probably the easiest way, though, to show that it is a homeomorphism is you look at f of x, you take its derivative, and it's quite easy to prove that it's a monotonic function. It goes from -infinity to infinity. So So being monotonic and going from minus infinity to infinity, it has to be 1-to-1 because it's monotonic. Because you can appeal to, what is it, Rolle's theorem, or is it Rolle's theorem? Or?
I remember that result.
Remember, if you've got 2 points if you've got a differentiable function, you've got 2 points the same, then somewhere in between, it's got to have a zero derivative.
It's strictly increasing.
This is a strictly increasing function. So there's theorems from calculus that tell that we can appeal to show that it's a bijection. We can. Why is it and its inverse continuous? Again, we can appeal to calculus because we're doing kind of arithmetic and we're doing nothing illegal, right? Because we're deliberately not doing -1 and 1, and this is positive, we're not dividing by 0. But actually, a simpler way to prove that both these are it's a bijection is, well, this is a monotonic function. It's order preserved. It's monotonically increasing, so it's order preserving. So it sends basis elements in here to basis elements there, and vice versa. So since basis elements are sent to basis elements, it has both, in both directions, it has to be a continuous function. And so that's a little bit of a simpler way. Okay. So here is a little bit of a perverse example. So this is an example of a bijection that's continuous, and it's not a homeomorphism because its inverse isn't continuous. So you really do have to, it's not good enough just to have one being continuous in one direction. So S1 is what we call the unit circle. S2 is the sphere. S3 is the etc. Higher dimensions. And you would have seen this before. This is kind of like a standard way to parameterize the circle, right? And it's closed here, right? Because if you have it open here, you're going to miss out on one point, and it can't both be closed because it won't be an injection. Okay. Now, why is the inverse not continuous? And you can see that because if you take an open set here, this half open interval between 0 and a quarter, remember it's open in this topology, in the subspace topology. When you look at its image, it's not open here. So therefore, the inverse is not continuous. Oh, that should have been an embedding, not an embedding, sorry. And a continuous injective map need not be an embedding, but for the same reason, because the inverse is not continuous. So if you, instead of thinking of this as going from this half open interval to S1, think of it going to R2. So you think of that as an embedding, you want to embed this into R2 by this, since the inverse is not continuous there, it's not a proper embedding. So these counter examples are always kind of useful. Okay, how much time we got? Oh, we've got no time left. Okay, so that's the boring stuff about how do you make more continuous functions. But that will do for today.